Swayam Prabha. Digital India. Educated India.
Now we are going to discuss the working principle of another neural network, which is known as the self organizing map, and in short this is known as SOM. Now, this network was proposed by Cohen around 1994-95, and according to his name, so this network is also known as Cohen network. Now, here we will see that, so this particular network actually we use the principle of unsupervised learning. So, that the concept of that unsupervised learning I am going to discuss in details. Now, before that, let us mention that this self organizing map can be used as a visualization technique or a dimensionality reduction technique, and that too this is actually a topology preserving tool. Now, let me discuss little bit what do you mean by the visualization technique or dimensionality reduction technique, and what do you mean by this topology preserving tool. Now, supposing that say I have got a data in higher dimension, say in 10 dimension, 20 dimension, something like this. Now, this data can be represented, higher dimensional data can be represented something like this. So, this is actually the representation of the higher dimensional data, a large number of data, and supposing that, so this data is having say L dimension, say higher dimension, say 20 dimension, 10 dimension or something like this. Now, this data we human being we cannot visualize. The reason is we can visualize only up to 3 dimension. Now, if the data is there in more than 3 dimensions, say 4 dimension or 5 dimension, we cannot visualize. So, for the purpose of visualization, so this particular higher dimensional data is to be mapped to the lower dimension, say in 2 dimensions, say x and y. Now, if I want to map this higher dimensional data to the lower dimension for the purpose of visualization, so we cannot do actually 1:1 linear mapping. So, we will have to go for some sort of nonlinear mapping. Now, this higher dimensional data, so we are going to map to the lower dimension for the purpose of visualization. That means, we want to see the relative position of the different points which are there in higher dimension. So, those points we are going to see in the lower dimension. Now, these techniques are known as actually the visualization technique and or the dimensionality reduction technique. Now, if you see the literature, there exist a large number of techniques for this dimensionality reduction. Now, this dimensionality reduction or visualization technique can be classified into 2 groups. Actually, we have got your, so we have got the dimensionality reduction technique, say DRT, dimensionality reduction technique, and these techniques can be classified into 2 groups. One is called the distance preserving tools. So, distance preserving tool, and we have got actually the topology preserving tool. So, we have got the topology preserving tool. Now, let us try to find out the difference between your the distance preserving tool and the topology preserving tool. So, by distance preserving tool actually what we mean. So, in a higher dimension, if I consider 2 points, so one point is here, another point is here. So, we can find out the Euclidean distance between them. Supposing this is point I and this is your point j, and this particular distance is nothing but say d I j. So, in distance preserving technique actually we consider only the Euclidean distance between them. but we do not consider the relative position of the jth point with respect to the ith point, whether the jth point is towards the left or towards the right or towards the top or towards the bottom with respect to this ith point, that is not considered in your the distance preserving tool. But in topology preserving, actually we are going to maintain the topology. That means, in higher dimension, if the jth point is towards top with respect to the ith, in lower dimension also. So, I am just going to map this point and this particular point. So, the relative position of these particular the points, the 2 points, those things will be maintained in the lower dimension, and that means in topology preserving. So, not only the distance, but we try to maintain the relative position of a particular point with respect to another point. Now, this self organizing map or SOM, that is actually a very efficient tool for your the topology preserving. Now, actually I should mention one thing, in human brain we use this type of network very frequently, and that is why actually we can remember the topology. For example, sitting at a particular place, we can say think. So, say for example, starting from here the road towards another city. So, what is the direction, how does it go from one city to another city. So, we can imagine that, because we have got the topology preserving tool, that is nothing but self organizing map in our brain. Now, this particular self organizing map can also be used as a very efficient clustering tool. Now, in this course we have already discussed the working principle of a few clustering tools like fuzzy C-means clustering, entropy based clustering, we have already discussed in detail. Now, the similar type of problem can also be given to this self organizing map, and this self organizing map is actually a very efficient clustering tool. And as I mentioned that here in this particular network we use the principle of unsupervised and competitive learning. So, here we do not use the concept of supervised learning, which we have already discussed. Now, let us see how to use the concept of this unsupervised learning or the competitive learning in this particular the self organizing map. Now, if I see the main task of this particular the network, so that is as follows. Supposing that I have got some higher dimensional data, a large number of data points. For example, say, so I have got say 1, this is the ith one and this is the nth one. So, I have got say capital N number of data points in higher dimension, say these are in L dimension LD, okay, and those particular data will be passed through the input layer of this particular the network, and our aim is to map these higher dimensional data, that is the L dimensional data, to the lower dimensional layer, and that is nothing but the competition layer for the purpose of visualization. So, what we do is each of these particular the n data points in higher dimension, we are going to map it to the lower dimension for the purpose of visualization. So, although this input layer is in L dimension, so this particular competition layer, or so this is nothing but the output layer. So, this output layer should be either in say 2 dimension or it could be say in 3 dimension. So, this could be your the 3 dimension, because we can visualize only up to 2 dimension or say only up to 3 dimension. So, these particular data points are to be mapped to the lower dimension, and that is nothing but the output layer or the competition layer. Now, we are going to discuss in details how can you do so this type of mapping from higher dimension to the lower dimension by maintaining the topological information of these particular the data points. So, these things actually we are going to discuss in much more details. Now, this self organizing map can also be called actually nonlinear generalization of principal component analysis. You might have heard about the principal component analysis, that is nothing but PCA algorithm. Now, this PCA is actually a very efficient tool for linear mapping, 1:1 mapping, but as we are doing the mapping from higher dimension to lower dimension, we cannot think of the linear mapping. So, we will have to go for actually the nonlinear mapping, and in this nonlinear mapping, so we will not be getting this 1:1 mapping, there will be some inaccuracy, and those inaccuracy we will have to actually accommodate. Now, here if you see, so this self organizing map consists of two layers. For example, say we have got the input layer and the competition layer. So, this is nothing but a two layer network, and on this particular competition layer actually there will be three basic operations, and those operations we are going to discuss in details. Those are nothing but the competition, then there will be cooperation, and after that there will be updating, and through this competition, cooperation and updating. So, actually this particular network is going to do the mapping from higher dimension to the lower dimension. Now, let us see how does it work. So, let us first concentrate on the competition. Now, the purpose of this particular competition is to declare a winner. Now, let us see how to declare and how to determine, so that particular the winner. Now, so this is the network. This is the network, although I have shown it here. So, this is the input layer and the competition layer, and I have already drawn this particular competition layer, but for the time being let me assume that. So, this particular competition layer is actually absent. So, this competition layer, actually these type of neurons are actually the way I have shown it here. So, those are absent for the time being say. Now, what is our M? Let me repeat. So, we have got capital N number of data. So, starting from 1 up to say capital N data points we have on the input layer, and they are in L dimension, that is your LD, or say higher dimension or any other dimension say. Now, so these particular data points are to be mapped to the lower dimension. Now, let us see how can we use the principle of, so this particular the competition. Now, let us see this the principle of competition first. Now, here as I told that we are going to map a particular data point, say ith data point lying on the input layer. Now, this particular ith data point, supposing that I am considering here m dimensional point. So, if it is having m dimension, so to represent this particular x I, so I will have to use x I 1, x I 2 up to x I m. So, I have got m number of numerical values, where I varies from 1 to up to capital N. So, this n is actually the total number of data points, and each point is having say small m dimension. Now, how to carry out? So, this particular the competition. Now, to carry out the competition, actually what we do is we generate at random some connecting weights between your, so this input neuron I and the neuron J lying on the competition layer or this output layer. Now, what we do is we generate some connecting weight or synaptic weight that is denoted by Wji. Now, if you want to generate, so this particular Wji, the first thing you will have to do is you will have to decide its dimension. Now, let me assume that once again this is having m dimension, that means the same dimensions of your this input data. Now, what we do is, so this Wji to represent, so what we will have to do, we will have to use small m number of numerical values, that is nothing but Wji1, Wji2 and the last is your Wjim, where j varies from 1 to up to n, n is nothing but the total number of data points lying on the input layer. Now, once you have got, so these particular the W values which are generated, now very easily I can find out what should be the equivalent distance between your xi and your this particular Wi. And through this competition, actually what we are going to do, we are trying to find out that value of W which is closest to your, so this particular the xi. Now, before I go for, so that particular calculation, I am just going to show, so your on the schematic view, supposing that this is the ith data point which I am going to map to the lower dimension. So, what we do, we actually generate all such W values. So, these are all connecting weights or the W values, okay. And these are actually your say Wji, and those actually the connecting weights are generated at random using the random number generator, supposing that in the normalized scale between say 0 to 1. Now, if this is the situation, then very easily I can find out the equivalent distance between your the ith data point lying on the input layer and your m number of or capital N number of W values, each W is having small m dimension. Now, how to do this? So, let me explain that. Now, as I mentioned that we are going to determine the equivalent distance between your xi and Wji, and this particular equivalent distance is nothing but is your xi minus your Wji square. So, this is nothing but the equivalent distance between xi and Wji. Now, corresponding to this particular your so ith data point, so we have generated how many W values? Capital N number of W values. So, how many such equivalent distances are possible? So, we have got capital N number of equivalent distance values, and out of these capital N number of equivalent distance values, so what we do is we try to find out which one is the closest, which one is having the minimum equivalent distance values, and that particular W which is having the minimum equivalent distance, that is actually declared as the winning neuron or the winning connecting weight. So, mathematically your the winning neuron or the winning connecting weight, that is denoted by small n, and your the equivalent distance between n and xi is expressed like this, and so this n is considered as your the winner, that means it is having the minimum of these equivalent distance values. Now, let me repeat. So, out of those equivalent distance values, we try to locate that particular Wji which is closest to your xi and which will give rise to the minimum equivalent distance values, and that particular Wji will be declared as the winner. Now, the purpose of this particular competition is actually to declare the winner of this competition. Now, if you just see on the your plot, so here, so once again corresponding to the ith one, so I am trying to find out the winner. Supposing that, so this particular the connecting weight is nothing but the winner. So, this indicates actually the winner neuron, and that is denoted by your small n. So, small n is nothing but is your the winning the neuron. Okay. Now, this is the winner. Now, surrounding this particular winner, so there will be some other connecting weights. Now, for the actually time being, so these particular neurons are not drawn, it is simply the connecting weight. So, these are simply the connecting weights, the neurons are not drawn now. Okay. So, surrounding this particular connecting weight, so we have got a number of other connecting weights in this particular your neighborhood. Okay. So, let me repeat, the purpose of this particular competition is to declare the winner, and once that particular winner we have got, now we can enter the cooperation. The next stage is actually your the cooperation, and here in this particular stage, so we have already decided the winner through competition, and surrounding that particular your the winner, there will be some excited connecting weights or excited neurons. Okay. So, let me just draw it here. Now, here if you see, so this particular surrounding that is expressed with the help of one mathematical expression, that is nothing but the Gaussian distribution. Now, if I just draw corresponding to this particular equation one Gaussian distribution, so it will look like this. So, this is actually the Gaussian distribution, and it is having your the standard deviation, that is nothing but is your sigma t, and it is having the mean. So, mean is nothing but the property of this particular the winner. So, the mean properties are decided by the winner's property, which have been declared as winner in your that particular the competition, and there will be a Gaussian distribution, and so this the nature of the Gaussian distribution, that will be decided by your the standard deviation, that is sigma t. T means the tth iteration. Now, if you see that H j n x I, so j is actually your excited neuron or the excited connecting weight, and small n is nothing but the winner. So, your the neighborhood function between the jth excited connecting weight and the winner small n at tth iteration is nothing but exponential minus d j n x I square divided by 2 sigma t square. Now, this particular d j n x I is nothing but the lateral distance between the winning neuron n and the excited neuron j. So, very easily you can find out. So, this particular your Euclidean distance, and once you have got this, now let us concentrate on this sigma t. So, this sigma or the standard deviation, it is not kept fixed, and it is actually a variable, and it will vary from your iteration to iteration. Now, here we have written, so this particular sigma t is nothing but sigma naught exponential minus t divided by tau. Now, this particular tau is nothing but predefined number of maximum iterations. Supposing that tau is kept equal to say 1000 or something like this. So, tau is say 1000. Now, so this is actually the fixed number. Now, as iteration proceeds, what will happen to this sigma t? So, as iteration proceeds, so small t is going to increase. Now, as small t increases, what will happen to this particular sigma t? So, this particular sigma t is going to be reduced. It is going to be reduced, and if sigma t reduces, what will happen to the nature? Now, if you see this particular nature, if sigma t reduces, so I will be getting some sort of steeper distribution of this particular the Gaussian. So, as iteration proceeds, so there is a possibility that I will be getting say this type of steeper distribution, and as iteration proceeds, I may get even steeper distribution corresponding to this. So, this type of steeper distribution will be getting. Now, if I take the plan view, say corresponding to the first your the Gaussian. So, there is a possibility might be this indicates the plan 1 plan view for the original. As iteration proceeds, so it is going to be reduced something like this, and there is a possibility. So, this particular neighborhood is going to be reduced, and we will be getting actually a lot of interaction, and through this particular interaction between your the mean properties, that is the winner, and your the excited connecting weights or the excited neurons. So, there will be a chance of updating of both the things. Now, this is almost similar to the situation like supposing that say in one institute there are a large number of professors and around under each professor a large number of students are working. Now, these students are all excited neurons or excited connecting weights, and as if the professor is having the mean properties and professor is the winner. Now, there will be lot of interactions between the professor and your the students, and through this particular interaction there is a possibility that your the students are going, their knowledge level are going to be updated, and at the same time the professor is also going to learn a few new things. So, through this particular interaction, so both the professor as well as the students are going to learn, and there will be some sort of updating. Now, the principle of updating is very simple. So, what we do is we try to update say w j I at t plus 1th iteration, and that is nothing but w j I t plus eta t. Eta t is nothing but the learning rate, and this h j n x I is nothing but is your neighborhood function, which I have already discussed, and this x I minus w j I t is nothing but the difference between your x I and your the w j I at tth iteration, and this particular learning rate is going to vary in the range of say 0 to 1, and through this particular interaction. So, both your the excited neuron or the winner as well as your the winner as well as the excited neuron. So, their conditions are going to be updated, their connecting weights are going to be updated, and through a large number of iteration. So, corresponding to that particular ith data point, if you remember, like on the input side we have got a number of neurons. So, this is the first one, this is actually the ith one, and this is your nth one. So, corresponding to this particular ith one, so actually we are going to get the updated one, and ultimately corresponding to this I will be getting finally. So, one connecting weight something like this, that is the modified winner. Now, you repeat the same process for the remaining your n minus 1 data points lying on the input layer. So, this is the input layer. So, lying on the input layer you repeat the process for your the same process inside a for loop in the computer program. So, corresponding to each of these particular the data points in higher dimension. So, I will be getting actually one modified winner w. So, for each of the data point actually I will be getting this particular the modified your the connecting weights. Now, once you have got, so this type of modified connecting weights, now we will have to do the mapping. Now, let us see how to do this particular the mapping. Now, let us try to actually understand the situation. So, on the input side or on the input layer we have got capital N number of data points, and for each of the data points in higher dimension I have got the modified winner connecting weights. So, I have got how many such w values? Once again I have got capital N number of w values. So, we have got capital N number of w values. So, what you can do is now this w is having the dimension. So, w is having the dimension actually your m dimension. So, what you can do is if I consider that m dimensional space, its origin is what? I have got actually small m number of zeros on the origin. So, we have got small m number of zeros on the origin, okay, and what you can do is I have got capital N number of the W values corresponding to capital N number of neurons lying on the input layer. Now, what you can do is starting from the origin. So, I can find out the Euclidean distance of all the W values, all capital N number of W values. Then how many Euclidean distance values we are going to get? So, we are going to get actually capital N number of Euclidean distance values. Let me repeat, starting from the origin in m dimension, like I have got 0 0 0 small m number of 0 at the origin. So, I can find out, I can calculate the Euclidean distance of capital N number of W's, and that means I can find out capital N number of Euclidean distance values. And once you have got capital N number of the Euclidean distance values, we do the sorting and in the ascending order. So, the W which is closest to the origin will be considered first, and we are going to do the sorting in your ascending order. And once you have got that particular information of Euclidean distance in the ascending order, so what we can do is we can consider that particular W which is closest to the origin, and its Euclidean distance we can consider as radius, and we can draw one circular arc something like this, that is denoted by C1. And the next Euclidean distance value I can use as the radius, I can draw another circular arc. Similarly, I am drawing another circular arc, and how many such circular arcs I will have to draw? I will have to draw capital N number of circular arcs. So, I am just going to draw capital N number of circular arcs. Now, let me concentrate on the first circular arc. You take a point at random lying on the first circle. So, let me consider this particular the point, and now I know the Euclidean distance between. So, this particular W, so this corresponds to one W, this corresponds to another W, the connecting weight. So, I know the Euclidean distance between this W and that particular W, and its numerical value I can calculate, and considering that as the radius, I can draw another circular arc, and supposing that I am drawing this particular arc. Now, once you have got, so this is another point. Now, considering this as the center and considering the next W, so I can find out the Euclidean distance, and this particular Euclidean distance we can consider as the radius, and I can draw one circular arc here. So, I will be getting another intersection point. Following the same procedure, I will be getting another intersection, another intersection, another intersection, and so on. And once you have got all such intersection points, those are nothing but the points in 2 dimension or the lower dimension. So, those higher dimensional data, now we are in a position to map to the lower dimension, like say 2 dimension, for the purpose of visualization. Now, if you just go back to the diagram which we have considered for the self organizing map, now we will be able to explain this, like corresponding to this, supposing that I have got only one winner. Similarly, corresponding to another data point might be another winner and modified winner. Say corresponding to this might be another, corresponding to this might be another. So, capital N number of data points lying on the input layer will be mapped to the lower dimension on the computation layer for the purpose of visualization. So, this is the way actually from higher dimension we can do the mapping to the lower dimension for the purpose of visualization. So, now we will be in a position to draw all such neurons here, and each neuron indicates a particular the point lying on this input layer. So, I will be getting here, so capital N number of neurons, and each neuron is going to represent a particular neuron in the higher dimensional input layer. Now, this is the way actually it works. Now, I can show one example, like very simple example, like this is actually one test function that is called the Schaeffer's test function. So, this Schaeffer's test function, if you see the mathematical formulation, so this is the mathematical expression for Schaeffer's test function, and here you see y equals to 0.5 plus sine square root summation I equals to 1 to 4 x I square minus 0.5 divided by 1.0 plus 0.001, then summation I equals to 1 to 4 x I square. So, this is actually the mathematical expression, and here you see I varies from 1 to 4, that means your this is in 5 dimension. Now, these 5 dimensional data we cannot visualize, because we can visualize only up to 3 dimension. Now, what we do? We generate 1000 data points at random lying on the surface of this particular the test function, and those 1000 data points are mapped to the 2 dimension for the purpose of visualization using the self organizing map. So, in higher dimension, if there are 1000 data points, in lower dimension also you will be getting 1000 data point, and here the topological information will be kept unaltered or intact, and here these particular data points are well distributed. So, there is an ease for visualization. So, very easily we can visualize these data points and their relative position or their topology, we can visualize very easily. Thank you.